atmosphere. We will discuss ionospheric measurements and some of the ionospheric phenomena. In the second lecture yesterday, we saw about the variations in the ionosphere as a function of time of the day, season, solar activity, etc., and also some few equatorial and longitudinal ionospheric phenomena like the SQ current and the electrojet current, and also the equatorial anomaly. Now, most of the ionospheric measurements depend very much on the effects of the ionosphere on the radio waves which are propagating through the ionosphere. And radio waves are a part of the electromagnetic wave spectrum. And therefore, today we will start with some discussion about the propagation of radio waves in plasmas like the ionospheric plasma. You know, electromagnetic wave is having an electric field component E and a magnetic field component B, which are both perpendicular to each other, and they themselves are perpendicular to the direction of propagation of the wave. Now, one type of electromagnetic wave is the plane wave, in which the electric and magnetic fields are confined to a particular plane perpendicular to the direction of propagation. So in that plane, the value of the electric field E can be written as a function of Z, the distance along the direction of propagation. So E varies with respect to Z, as given by this equation, that E of Z is equal to the real part, that is that R represents that of E0 into e to the power of I omega t minus k z. This represents a wave equation. Now the E0 is the amplitude of the wave, and omega is the angular frequency of the electromagnetic or radio wave, and k is what is called the propagation vector or the propagation constant. This equation simply shows that the value of E varies sinusoidally with respect to Z, and also at a given point, at a given value of Z, it will vary sinusoidally with respect to time. The frequency of this variation is decided by omega, and the wavelength of the wave is related to the propagation constant k, such that k is equal to 2 pi upon lambda, the wavelength. Similarly, the frequency, angular frequency omega, is related, as all of you know, to the linear frequency by the relation omega is equal to 2 pi times the linear frequency f. Now, in the free space, the electromagnetic waves propagate with a velocity of light, that is c. All electromagnetic waves propagate with the same velocity c in free space. But in a plasma medium like the ionosphere, the propagation velocity is less than c, and the ratio between the velocity in the medium to the velocity in free space, that is c, is known as the refractive index or the index of refraction, which is given here by the formula refractive index or index of refraction n is equal to c, that is the velocity in free space, into k, propagation vector, divided by the angular frequency of the wave. And it is a complex quantity, and therefore it has a real part mu and an imaginary part chi. It is the real part which contributes to the propagation of the wave, and the imaginary part leads to absorption of the wave in the medium. Now we can consider a few simplifying situations. For example, the plasma is considered as cool. That means temperature effects can be neglected, and there are no collisions between the particles in the plasma, or in a different sense, we can say even if collisions are there, they are much more few. Collision frequency is very small compared to the wave frequency. And we also assume there is no external magnetic field applied to the medium. In fact, this is not true for ionosphere because we know the ionosphere is embedded in the Earth's magnetic field. That complication we will see later in the next slide. But now, under these three assumptions, the real part of the refractive index mu satisfies the equation mu square is equal to 1 minus x, where the x is called a magneto-ionic parameter, which is equal to the plasma frequency Fn square divided by the wave frequency f square. So mu square becomes 1 minus Fn square upon f square. And the Fn square itself is related to the electron density, n, number of electrons per unit volume in the medium, by the formula Fn square is equal to some constant kappa times the electron density, n. So the refractive index square now becomes 1 minus kappa into n upon f square. Kappa is a physical constant depending upon the density of the electron, the epsilon naught, that is the permittivity of free space, mass of the electron, and so on. So it has a constant value around 80. Now the propagation can be considered under different situations. The propagation near the speed of light. The propagation will be almost at the speed of light when the plasma frequency is much less than the wave frequency f. So almost it propagates as if in free space. So under that condition, if Fn is almost equal to f, then the mu will be approximately equal to 1. That means practically there is no refraction. So it moves almost like the speed with the speed of light. Now, when the plasma frequency F1 approaches the wave frequency, under that condition, the mu tends to 0. When plasma frequency approaches wave frequency, mu tends to 0. So, in that situation, the propagation is dramatically slowed down. And under the condition when the plasma frequency is exactly equal to the wave frequency f, from this formula, you can find that under that condition, the refractive index or index of refraction mu will be equal to 0. So that is the situation when a radio wave gets reflected from a medium like the ionosphere. So if you send a radio wave of a frequency f, it will travel through the ionosphere up to a height where the wave frequency is equal to the plasma frequency Fn, and from that height that will be reflected back. This is the basic principle that we use in probing the ionosphere or getting some information about the electron density in the ionosphere. Now we will now include what will happen if the magnetic field is considered. So in that case, when the magnetic field is there surrounded by the plasma, then the plasma is called a Magneto-plasma, and it is birefringent. That means the index of refraction depends on the polarization of the radio wave. We know there are two polarizations, the ordinary and the extraordinary, or the right circular polarization and left circular polarization. So the different polarizations have different index of refraction. Another property of the magnetoplasma is it is anisotropic. That means the index of refraction depends on the direction of propagation of the wave. That is, depends on the k. So under this condition, when we take into account the effect of the magnetic field, the index of refraction can be written by a more complicated formula. Mu square is equal to 1 minus 2x into 1 minus x upon again 2 into 1 minus x minus y t square plus or minus under root something. Now here we have yt and yl. Here you have yl, here we have yt. So what are these? So the yl is the longitudinal component of y with respect to the direction of propagation, that is along the direction of propagation, and yt is the component which is transverse to the direction of propagation. And then what is y? Y is here represented as a vector quantity because it depends on the magnetic field B. So it is B into E upon m omega. So B being a vector quantity, Magnetic field is also a vector quantity, that is therefore Y is a vector quantity, and it can be therefore resolved into two components, the longitudinal and transverse component. And in this equation, this plus and minus, they refer to the ordinary and extraordinary polarized radio waves. And the magnitude of Y is given by ratio of FH, that is the gyro frequency and the wave frequency. All these gyro frequency and plasma frequency, all these are typical characteristics frequencies of a plasma. Now, in this situation, when the magnetic field is also included, again, the ordinary wave will get reflected from the point where the plasma frequency is equal to the wave frequency. That is, this condition is same as that for when there is no magnetic field. Or in other words, the ordinary wave is not affected by the presence of the magnetic field. Now, the extraordinary wave has two conditions of reflection, x is equal to 1 minus y or x is equal to 1 plus y. When either of these conditions are satisfied, the extraordinary wave will get reflected. So these are the basic plasma or radio propagation parameters which will be used in instruments like the ionospheric sounding or Ionosonde. Let us now see, this is one of the classical and fundamental equipments, the Ionosonde, to study the behavior of the ionosphere. So the Ionosonde is an instrument for ionospheric sounding. That is, you are sending some radio wave, it gets reflected from the ionosphere and you are getting it back. That is called sounding. There is similarly in sound waves, there is echo sounding. You send you shout from here, far away if there's a hill, then the sound will go and reflected and come back, and you will get it as an echo. Similarly, here radio wave is used. So the transmitter TX, marked in this adjacent figure, transmits short pulses of radio energy into the ionosphere. Then, as we saw just in the previous slide, when the condition for reflection is satisfied, from there the wave transmitted by the transmitter gets reflected back towards the Earth, and then it will be received by the receiver Rx, and the receiver records the time delay between the transmission and reception of the pulses, and this time delay is proportional to the height from which it is reflected. That we will see a little later. So in this instrument, by varying the carrier frequency of the pulses, the time delay at different frequencies is measured and recorded. This record is usually presented in the form of a graph, and it is called an ionogram. Just a moment. So the ionogram is something like the cardiogram. So if you have some problem with your heart, then you will go to a doctor and he will advise to take a cardiogram. By studying the cardiogram, what is the exact problem with the heart, that can be understood. Similarly, by studying the ionogram, the characteristics and situations in the ionosphere can be studied. So this is the similarity of the terminologies. Now, from the analysis of the ionogram, several important characteristics can be found that play a significant role both in the studies concerning ionospheric physics and for radio communication purposes. So we talked about ionogram. The graph here shows a typical ionogram, which is a plot of the virtual height from which the wave is reflected versus the frequency of the transmitted wave. So by varying the carrier frequency of the pulses, typically from 1 to 20 megahertz, the time delay at different frequencies is recorded, and that record is the ionogram. This record is referred to as vertical ionogram or vertical incidence ionogram, and is usually presented in the form of a graph as shown here, where normally in place of time delay, actually this y-axis is proportional to the time delay, as given by this equation. The h dash, I said virtual height. I will just explain it now. H dash is equal to c, the velocity of light or radio waves in free space, multiplied by delta t, the time delay, divided by 2. Because here we assume the radio waves traveling with the velocity c during this time delta t. So the total distance covered during delta t is c times delta t, and during that time it has gone up to a height and then got reflected back. So that is twice the height. Therefore, divided by 2 will give the height. So because we assume it is traveling with velocity of light c, it is not actually true. So this is called the virtual height. It is not the real height from which that particular wave is reflected because of this assumption. That can be corrected, and that there are techniques for that. So delta is the time, delta t the time delay, is dash is the virtual height, and c is the free space speed of electromagnetic waves. So because we assume free space speed, but actually it may be traveling with a different velocity because ionosphere is a plasma medium. So in this ionogram, as you see here, these traces, see, depending upon the height from which different frequencies are reflected, this trace takes a shape. So this initial trace near about 100 kilometer altitude is corresponding to the E region of the ionosphere, and wherever this cusp occurs, that is called a critical frequency. Here it is marked as FOE. Now the subscript O referring to the ordinary wave. The extraordinary wave may have a different trace, we will see now. So the FOE is the critical frequency of the E layer, the frequency at which this cusp occurs, here between about 2 to 3 megahertz. Now similarly, where the E region trace starts, that is the H dash E, that is the virtual height of the E layer. Now above that you get a reflection corresponding to the F1 layer. So again you get a sort of cusp, and wherever that cusp occurs, that is the critical frequency of the ordinary wave of the F1 layer. Similarly, this is the height of the F1 layer. The meaning of the critical frequency is that is the maximum frequency that can be reflected by that particular layer. So similarly, you get a trace corresponding to F2 layer. So you have got FO, F2, critical frequency of the F2 layer, and H dash F2, the virtual height corresponding to the base of the F2 layer. So there are two traces here. The first one where we have marked the FOs, that is the ordinary, and the second trace is corresponding to the extraordinary. Because the reflection conditions are different for ordinary and extraordinary, the traces are separated, and the corresponding critical frequencies are also different. For example, we can define this as the FX F2, that is critical frequency for the extraordinary component of from the F2 layer. Okay, so with this you can study the ionosphere, how the frequency varies with height, and the frequency is in turn related to, because the frequency which is reflected is equal to the plasma frequency, and plasma frequency is proportional to the electron density. Therefore, we can convert these frequencies of reflection into corresponding values of electron density. Thereby, you can get a idea of how the electron density varies with height, or you can get the electron density profile. Now, the limitation of the Ionosonde is that it cannot probe the topside ionosphere above the F region peak. Yesterday we saw the classification between bottom side and top side. That is because if you increase the frequency of the transmitter beyond the critical frequency of F2 layer, that is the maximum electron density in the F2 layer, then the radio wave will not get reflected, but it will be simply transmitted. So you won't get any echo back. Therefore, it's not possible to study the region above the F2 peak. That's a limitation of the Ionosonde. One way it can be taken care by putting an Ionosonde on a satellite, and then the satellite orbiting at an altitude of over 1,000 kilometers or more. Then you can sound the ionosphere from the top, from that satellite, and get an idea, a similar thing, a replica of this from the top side. So that is what is called topside sounding or topside ionogram. And if you have both together, then you can study the complete electron density structure in the ionosphere. In fact, such satellites were there, like Elevate, the Canadian satellite, then ISIS, Ionospheric sounding satellite. So all these were taking measurements, and a lot of information about topside ionosphere has been obtained from that technique. And this Ionosonde is being operated worldwide. Maybe there are about 200 or more Ionosones distributed throughout the world, and they are automatically taking the ionospheric measurements or ionograms at a predetermined interval, sometimes 15 minutes, sometimes 5 minutes, like that, depending upon the need. And from this worldwide ionograms, the condition of the ionosphere on a global scale can be always understood, and by automatic data analysis and programming, almost a real-time situation of the ionosphere can be obtained, which can be used either for studying the physics of the ionosphere or for helping the radio communication or broadcasting people. Now, another technique which is very powerful, but at the same time very expensive, is what is called the Incoherent Scatter Radar. The map shows only there are few locations, 7 or 8 in the whole world, where this instrument is there, and the bottom picture shows the different kinds of antenna system in the various incoherent scatter radar setups. So it can measure almost all ionospheric parameters, not only the electron density, but the electron temperature, ion temperature, the movement of the ionosphere with some velocities. Then like that, many parameters can be measured. It's a very powerful technique. Measurements up to a height of about 1500 kilometers can be obtained. So this picture shows the antenna system of some of the incoherent scatter radars. This is, for example, Arecibo, which is near Puerto Rico. It is operating at 430 megahertz. So this is a very big antenna system, and this is a natural limestone mining hole has been used for fixing the antenna. And then the antenna feed points are all controlled remotely, and so it's a very complicated and powerful system. The requirement here is that what we are actually doing is a very powerful radio transmitter is there. It is pumping extremely large powers into the ionosphere. Then from the individual electrons in the ionosphere, by a process called the Thomson scatter or incoherent scatter, an extremely small fraction of the transmitted power is returned back to the receiving system. And this fraction of the power which is returned is represented by the scattering cross-section of the electrons, which is very small, something like 10 to the power of minus 28 or 10 to the power of minus 30, with the result that only such a 10 to the power of minus 28 part of the transmitted power only is sent back. So and each electron is scattering independently, and therefore the scattered signals are incoherent, and that further weakens them, and we have to do a lot of data processing to infer or to derive the required parameters from that. So this is governed by the radar equation. The received power, which is very small, PR, is equal to the transmitted power, PT, into G is the gain of the antenna square, the scattering cross-section of the target. So if it is ionosphere, it is the free electrons there, which is the target. Then the wavelength lambda square, and then 4 pi cube, and then this is very important, the range R, that is the distance from the transmitter to the target, to the power 4. So it is inversely proportional to range power 4. So farther away from the ground, the ionospheric point from where we are trying to get signal, the R will be very large, so R power 4 will be much larger, so the power will be extremely small. So that limits the maximum height from which we can get measurements. So the all parameters are listed here. So this, though it is extremely small power with sophisticated signal processing techniques. It can be recorded, and a lot of studies about that can be made. So there are also locations like ISCAT, this is European Incoherent Scatter Radar, which has a UHF as well as VHF component. Then Jicamarca near the magnetic equator, there is a radar which is operating at 50 megahertz. So on and on. So this is a very powerful technique. So it's a typical result of what can be obtained from there. This first block shows the electron density variation with respect to height. Say from a height of about 100 kilometer up to about 1000 kilometer, the electron density is measured, and the points are the actual measurements. And so you can reconstruct the electron density profile, find out where the maximum H max is, as given HMF2 is 317.9 kilometer. What is the maximum electron density NM? It is 1.09 into 10 to the power of 12 per meter cube. Similarly, many other parameters can be obtained, and the observed points are fitted by a alpha Chapman layer here. So we see that the Chapman's theory fits very well with the observations using this technique. And in the middle panel, we show the TE, that is the electron temperature, how it varies with respect to height. One point we should remember now is that the plasma has three components: the neutrals, the electrons, and the ions. So of which the electrons have maximum temperature, and the ion temperature is smaller than that. Then the neutral and ions are always in collision with them, so they come to a sort of thermal equilibrium. Therefore, the neutral temperature is almost equal to the ion temperature, but the electron temperature is consistently higher. So the solid line in the center panel and right panel show respectively the linear fit for the observed TI, ion temperature, and TE measurements. This slide is taken from the work of Liu. Okay, so we have discussed the two interesting and important techniques. There are also other measurement techniques. One such is called the coherent backscatter radar. So here the backscattering signal is obtained not from the individual electrons, but the refractivity structures or refractive index structures which takes place in the medium. For example, if it is ionized medium, the electron density is not uniform. If it has fluctuations within that, say n plus or minus a delta n, then these fluctuations will produce corresponding fluctuations in the refractive index, and that will scatter the radio wave, not reflect. What we study the Ionosonde is based on the reflection. Incoherent scatter is depending on scattering by individual electrons. This is scattering by electron density structures or irregularities in the medium. We have one such similar radar which is called MST radar at Gedanki in southern India. So it can study not only the ionosphere but also the mesosphere, stratosphere, and thermosphere. That's why it is called MST radar. Then another technique is the radio beacon satellites. That means there are some satellites orbiting at the height of 1,000 kilometers or so, and they are constantly sending a radio signal from there. This signal can be received at many places on the ground, and as the signal propagates through the ionosphere, some changes in its characteristics take place. They can be measured, and from there, inference about ionosphere can be obtained. For example, the typical parameter measured by this experiment is the total electron content, about which we said yesterday. Similarly, another similar satellite is GPS satellites, which are at a much higher altitude of about 22,000 kilometers. So they are visible over a long time, over a location, and they are used both for navigation as well as ionospheric studies. So the advantage of this satellite technique is that it quickly passes through and completes its one global orbit in about 100 or 110 minutes. So a quick spatial coverage can be obtained using such satellite measurements. You cannot set up ionosodes at every location or even in remote places like oceans and other things, but this satellite technique will take measurements over such places. Then there are also other methods called in situ, that is on-the-spot probes to probe the electron density or the probe the temperature or the probe the composition, that kind of parameters, which can be again put on orbiting satellites. So at the orbit of the satellite, what is the parameter that can be measured by these techniques? Another is sounding rockets. So in this, at a given from a given rocket launching station, a rocket is launched and it carries some instruments or probes to measure various parameters. So that is also in situ measurement. Wherever the rocket reaches at that point of time, at that point of space, what is the parameter that is measured? So to get a quick vertical profile of the parameters, you can say it's like a snapshot of the Ionosonde at a given time. So the whole rocket flight finishes in about a few minutes. So during that time, how the parameter varies with height. Typically, rockets rise up to 150 kilometers. So up to that region, what is the vertical profile that can be studied? There are also other radio propagation experiments like absorption. We said the imaginary part of the refractive index leads to absorption. So that can be used for measuring radio absorption in the ionosphere. Then the drifts, the movement of the ionization in the ionosphere. Then there is instead of total reflection, partial reflection occurs in certain conditions. From that, certain measurements can be done. So like that, there are a host of techniques. Okay. Now we pass on to some of the phenomena in the ionosphere. For example, the solar flare is a phenomenon occurring in the sun, but it has its repercussions, its effects on the ionosphere. What are they? That we will see now. So what are solar flares? They are sudden increases in the solar emissions or brightness or intensity at certain wavelengths, particularly the X-ray wavelengths. They are classified based on their X-ray brightness or intensity in the X-ray emission in, say, typically 1 to 8 angstrom or 0.1 to 0.8 nanometer wavelength range. And so if the intensity I or the brightness I, based on that, based on its value, the flares are classified into 4 categories. The X-class flares, where the intensity is more than 10 to the power minus 4 watts per meter square. So if you look at this graph, what it shows is the X-ray flux or X-ray intensity or brightness measurements. The blue graph shows in a particular wavelength band 0.5 to 4 angstrom units, and the red graph shows in another wavelength band that is 1 to 8 angstrom unit. Both curves are almost similar. So you see, for example, here at this time, there is a sudden spiky increase of the X-ray flux, and that is a solar flare. Now, according to this classification, if it exceeds this 10 to the power minus 4, because this is exceeding that, it is 2 into 10 to the power minus 4. So it is therefore called a X2 class flare. Only this one, this is between 10 to the power minus 4 and minus 5. So it is called a M class, moderate class flare. And so the actual brightness is 5 into 10 to the power of minus 5 watts per meter square. So on and so forth. This is a very strong flare, X6 class. And so that flare is called a Bastille Day event. Just like meteorologists classify the storms with different names, characterized with different names, these flares are also classified with some names depending upon the day they occur and the intensity and so on. So this is called a Bastille Day event, which occurred on the Bastille Day, which is 14th of July, and which is some religiously important day and called Bastille Day. So it is Bastille Day event. So this kind of flares occur, and in fact, much stronger X10 and X17 class flares were seen in the October-November 2003 period, and they are called Halloween storms, just another name. Now, what happened during the flare is pictured here. So, the flares are usually associated with active regions or sunspot numbers on the sun. Sun has an overall average magnetic field. In addition to that, at the sunspots, magnetic field is very strong. So here, a sunspot with north magnetic polarity and this is south magnetic polarity is shown. So obviously between these north and south magnetic polarity, magnetic field lines will be like this, will be arcing like this. So the plasma has a characteristic, it will move back and forth along the magnetic field lines. This is the solar coronal plasma. Or this is actually in the chromosphere, and this is the photosphere. So chronospheric plasma will be moving, and then they will get accelerated, and by that acceleration process, a process called bremsstrahlung, some radiations can be emitted like the H alpha radiation. Similarly, there are electrons. Here, how the electrons came. So the magnetic field polarity is, say, this is a south magnetic polarity. So field lines are coming towards that. And this is a north magnetic polarity. Field lines are going away from that. So here is a region where opposite polarity magnetic fields are almost touching each other. And therefore, there is a reconnection taking place, or a neutral point is occurring. Magnetic field is getting neutralized, getting nullified, and then the magnetic energy is converted to plasma energy. So taking that energy, the plasma is ejected out, and that is a plasma emitted from the solar atmosphere. Similarly, there are the charge particles here. They get accelerated. Say electrons get accelerated towards the photosphere, and then when these very energetic electrons, when they come and hit the neutral atoms or molecules here in the chromosphere, then that is the basic mechanism of production of X-rays. When a energetic charge particle is stopped by a material particle because of the strong deceleration taking place, X-rays are emitted. This is what exactly happens in an X-ray machine that we use for medical diagnostics and so on. So by this process, X-rays are emitted, H alpha is emitted, some plasma is emitted. So electrons are traveling this way, some protons are traveling this way, so protons are also emitted. So in flare, all these kinds of things are emitted, and in large quantity. And so that is what is happening. And the number of flares, NF, at any time is proportional to the sunspot number R minus 10. So there is a correlation between sunspot number and the number of flares. That means during high solar activity period, more flares are expected. Therefore, more such events will be taking place. This picture shows how the flux of protons associated with a, not all flares are associated with a proton flare, but some will have proton flare. And then this is the flux of the 10 MeV protons. This is the flux of the 30 MeV protons. So how it increases, and then after some time it dies back. So these protons also travel. The electron, the X-rays and H alpha radiation, they also travel, come towards the Earth. And when that increased intensity comes, we get the effect of that flare on the ionosphere and other mediums. So these radiations, X-rays and particles coming, so they will produce what they will produce. So the enhancement in the different wavelength bands, so for example, 2 to 10 angstrom unit, how much was the quiet time value of the flux, how much was the increase during the flare, that is listed here in various wavelength bands. So these 1, 2, 3, 4, 5, 6 are different wavelength bands. And because of that wavelength bands, because of the basic photoionization process that we have learned, the ionization increases. This is the delta Ne, increase in ionization, say at about below 100 kilometers due to the large X-ray flux. The 2 is for long X-rays, 10 to 100 angstrom units. So they produce something in the E region. Then similarly, the EUV fluxes, they produce excess ionization in the F region. So at different heights, different wavelength radiations produce enhancement in the electron density. So that is what is shown here. And this is actual measurements. The other one is computed. We have the measured flux in enhancements. Therefore, how much electron density enhancements will occur, that is computed. That was the previous diagram. Here, this is actual measurements, electron density profiles before and during solar flare measured by the incoherent scatter radar technique that we described some time back. So the electron density profile from about 100 to 250 kilometers is shown here. So one is the pre-flare profile, 2, 3, 4, etc. profiles where you see consistent increase because of the excess ionization coming from the sun in the electron density. So these are like that. Now, another effect of this flare is that this excess ionization produced, as we saw in the previous slide, they are mostly in the lower part of the ionosphere, say below about 200 kilometers. There the excess ionization is taking place, and because of this excess ionization there, the D region gets very much enhanced in electron density, and the D region is the region which is responsible for radio wave absorption. So therefore, the radio waves that we transmit in a ionosonde to get reflected from the ionosphere, they get absorbed by the D region ionization, and therefore they are not able to travel up to higher heights and get reflected from the E region or F region. So therefore, here, if we look at this is a standard ionogram, you should get a trace, something corresponding to E layer, something corresponding to F1, something corresponding to F2. But when a flare occurs, because of the heavy absorption in the D region, the frequencies which are to be reflected from E region or F1 region, they are not propagating upward to that region because they are getting absorbed. So there is no trace of the reflection from E or F layer. So that is why frequency below about 9 megahertz, they are not reflected because they are getting absorbed by the excess ionization produced in the D region. So you get a trace of the ionogram only above certain frequency, which are not affected by the region ionization. So this is the typical thing. This graph actually is an extrapolated electron density profile computed somehow from the actual measurement and something extrapolated for there is no measurement. So actually here we can see that this is the real height profile derived using some computer program. So the real height is always lower than the virtual height. So the point here is excess ionization produced in the ionospheric D region between 50 to 90 kilometers by the enhanced X-ray emission causes radio wave absorption, whereby frequencies below 9 megahertz are absorbed in region and do not travel up to F region to get reflected from here. Okay, now we pass on to another phenomena, which is the solar eclipse. Now this is the opposite of flare. Flare, there's an enhancement of the radiation takes place. Here, the radiation coming from the sun is shadowed or is cut off, is blocked by the moon, which comes between the sun and the earth, and therefore a shadow of the moon is falling at some spot on the earth, and because of the movement of the moon and the sun, the moon and the earth, the shadow also moves with respect to time, and then you get a ground track, which is called the path of total solarity. So this is the situation in a total solar eclipse when all of them are perfectly aligned. So with the result that a certain point on the surface of the earth, they are now not getting the solar radiation. So naturally they are at the ionosphere above that spot, solar radiation is not coming. So the ionospheric density or production will decrease. So this is what is seen that say if you look at the critical frequency of the E layer, so it slowly decreases. The arrow shows where the eclipse occurred, the totality of the eclipse occurred at time. So it started slowly decreasing, and then once the eclipse effect is over, it lasts only for a few minutes to maybe less than an hour. And once that is over, then the parameter recovers, electron density in the layer recovers. So the time is very high resolution, 801, 901, etc. So the decrease lasts for a short while and then it recovers. Similarly, the electron density at 220 kilometers, 300 kilometers, different heights it is measured. Everywhere you see a decrease, and the decrease is more and more delayed as you go to higher and higher heights. So the response time of the higher regions is more. So the radiation is cut off here, but its effect is seen after some time delay, which increases with height. Similarly, FO, F2 is shown by this dashed line that also shows some effect. And here, in fact, dashed line is the normal FOF2, and this is the FOF2 during the fire event. So it decreases in electron density in the ionosphere take place because of the sharp cutoff of the solar radiation during eclipse. Now, this is again a total profile from about 100 to 800 kilometer measured during before the eclipse is profile 1 at totality and after the eclipse. So at totality is the curve number 2. So here at the peak of the F region, you see an increase in the ionization, which is somewhat surprising, whereas at the lower heights below 200 kilometers, you see a decrease. So this is nothing but it is not that there is a reverse effect taking place in the F region. F region is not very much controlled by the sun. It is controlled by dynamical processes. We talked about the transport and diffusion loss process. So they get affected in a different way during eclipse. That is why F region behaves somewhat different from that of the lower E regions. So nevertheless, there is some change in the electron density profile as a result of the eclipse. Now coming to mid-latitudes phenomena. Yesterday we saw some low-latitude phenomena like SQ current and equatorial anomaly. Here I would like to describe some mid-latitude phenomena. In fact, this circle is to highlight this decrease of the electron density. It should have been here, but I am not able to edit it now here. So this shows the mid-latitude electron density as a function of latitude, 45, 50, 75 degree latitude. So at night time, the electron density of course normally should decrease, but it decreases much faster or at this latitude belt. And then after some latitude, it recovers. This is spatial variation. So there is a region here where the electron density is drastically less, and that is why it is called a trough. A trough is, a crust is an increase, trough is a valley-like thing is created. So this is a nighttime phenomenon which marks the transition from mid to high latitudes. Typical, its location is 55 to 65 degree magnetic latitude. The reasons seen to this are stagnation region, that is plasma has been convecting throughout the night side in the absence of ionizing source, and hence it is decaying. Then that is transport processes. It is getting convected away, and there is no new ionization being produced. So there is a decaying. Then frictional heating leads to field-line transport because at high latitudes magnetic fields are almost vertical. So the plasma is lost along the field line transport. Then similarly, enhanced plasma motion with respect to neutrals, some sort of frictional motion between neutrals and ions, that leads to chemical and dynamic loss process. So these are the possible mechanisms for the production of this. And some more details about this are here. For example, the equatorial edge is located at about 50 to 51 degree of latitude. Position of the poleward edge of the trough is considered to be connected with there is a magnetosphere. We have not touched upon it yes, but there also is a plasma pause. There is a transition between ionospheric plasma and magnetospheric plasma. So this coincides, the location of the equatorial edge coincides with the plasma pause boundary. So and in fact that connection is through magnetic field line. So Izengawa in 2005 showed that these two features, the plasma pause and the mid-latitude trough, they are lying on the same field line. So that is now a sort of a global picture of this is shown here. This is the electron density variation versus in latitude versus magnetic local time. So here say during that time electron density is high, but and this is the dashed lines indicate the position of the trough, which is this is the northern hemisphere, this is the southern hemisphere. So it has some dynamical effects. It is not constant, but it varies with respect to geomagnetic activity conditions. The dashed lines denote the trough minimum position. The contour lines are electron density contours in log scale, log to the power 10 of Ne. electrons per centimeter cube is the unit used. So if the number is say 4, that means there are 10 to the 4 electrons per centimeter cube along that contour line. So, it is highly sensitive to the geomagnetic activity because it is connected with the magnetosphere and magnetic field lines. So obviously, there's a geomagnetic activity that will affect. So another interesting feature which occurs at high latitudes or in the polar region is the polar cusp or cleft, which occurs forward of the last closed field line on the day side. So the picture here shows the magnetic field structure of the Earth, which is distorted from the normal dipole configuration because of the interaction between the solar wind plasma, which is coming all the time from the sun, and the Earth's magnetic field. The magnetic field gets distorted. So on the day side, it is compressed like this, and on the night side, the field lines starting from polar regions are stretched towards the night side. They do not form closed field lines, and the ones which are nearer to the Earth, they have closed structure, but they are somewhat distorted from the normal dipole structure. So this kind of distorted field line structure finally confines the Earth's magnetic field into a cavity shown by this dashed line, and that cavity is called the magnetosphere. For that we will study maybe in the next lecture. So because of this geometry between the last closed field line on the day side and the first open field line on the night side, there is a region where through which no magnetic field passes, and therefore the plasma can find a easy entry into the ionosphere. Therefore, this region shows increased ionospheric plasma density created by plasma flow from the magnetosphere. So therefore, plasma density in the ionosphere increases and gives rise to this feature of the cusp or cleft. Now we discuss some transient features in the ionosphere as seen from the ionograms, and here we are showing the feature what is called equatorial spread F. So equatorial means it occurs mostly in equatorial region. Of course, there are also spread up at mid-latitude, but the reason for that is different. It is called spread up because the F region trace is not a very sharp trace as we should be for a normal ionogram like this. But you see there are other features, other signals coming from the ionosphere as indicated by this patchy occurrence here. It is here, it is here like that. So this kind of additional feature, patchy type of trace is due to the presence of some kind of ionospheric irregularities which are scattering the radio waves in addition to the normal trace which is due to the reflection. So mostly this occurs during night time. As you can see here, this is 2015 also at night. This is 2115. So at night. These are taken on 11 February 2004. 11 to 12 February, during that night between 11 and 12 February is this one. So we see this feature exists up to about 4 o'clock in the morning, and then it becomes very weak, and then by next day the normal trace again restarts. But this is the early morning trace like that. So this additional feature which occurs occasionally due to plasma irregularities is called spread up, and one which occurs in the equatorial region is equatorial spread up. Now the effect of this kind of plasma irregularities can also be studied using another technique which is called very high frequency scintillation. So in this case, say a very high frequency signal at 244 megahertz is transmitted from a satellite at a height of about 1,000 kilometers or more, and then this frequency being very high compared to the plasma frequency or critical frequency of the ionosphere, they are not reflected, but they simply travel through the ionosphere and reach a receiver on the ground. But while traveling through the ionosphere, because of the presence of these plasma irregularities, the signal is not having a steady or a constant value, but it starts fluctuating. It starts. It starts. What happened? Yeah, the signal starts fluctuating from its mean value, and these fluctuations are called scintillations, and they are due to the presence of plasma instabilities or ionospheric irregularities. So this is another manifest of the ionospheric irregularities. Now we look into another feature called sporadic E, which occurs in the E region, and it occurs not regularly or sporadically at times. That's why it's called sporadic E. So the feature that we see here on the ionograms, or say this one, where the E layer, in addition to the normal trace, which should be something like this or something like this, there is a enhanced signal coming from over an extended range of frequencies, and but it is not due to a total reflection, but it is again due to scattering by the presence of plasma irregularities present in the E region of the ionosphere, and since it occurs mostly in the equatorial region, it is called ESQ, sporadic E of the equatorial region. So these are the typical nature of that. And here, after some time, it disappears. ESQ disappears at 10:45, and then it is not there up to long time. After about 17:15, it again reappears. So that is why it is sporadic. Sometimes it is there, sometimes it is not there. So there are well-known plasma instability mechanisms like the two-stream instability or the gradient drift instability, which is causing this kind of plasma structures in the E region. And this ionogram here, pair of ionograms, shows a slightly different feature. This is similar to this one with the ESQ type of irregularities here at 9:30 hours, whereas this at 12 noon has a different feature. The E region structure, they are extended over a much longer range of frequencies, and because of this presence of these structures, we are not getting any echo from the F region of the ionosphere as should have been here. Whereas you see here you see the F1 region echo here. This is due to the F2 region. So here that F1 region echo is not coming. This is because the frequencies corresponding to the reflection from F1 region are not allowed to cross through this VS layer, and so they are blanketed by these irregularities. They are not reaching F region. Therefore, we are not getting any echo of that. So this is the type of sporadic key, which is called blanketing sporadic key or ESB. Okay, so these are the two features of F region and E region due to mainly presence of irregularities or plasma instabilities. Now, this is also shows in a bit more detail the Q type of blanketing sporadic key. The Q type of sporadic key in this ionogram, and this also Q type of sporadic key. And this is the blanketing, very, very strong blanketing type of irregularity, because of which the F region trace is completely absent in this. That means all the frequencies which should normally be reflected from the F region are getting blanketed or obstructed by the ionospheric irregularities at E region. And it's so strong that you get multiple echoes of that. So that is very, very strong case of blanketing sporadically. And these ionograms show the spread up. Here also there is some signature of spread up, and here also spread up. Here again, the upper one is not another layer, but it is the second echo or second reflection from the same F layer. So the trace is spread, and we have the features of spread up here. Now there are some recently discovered, maybe over the last 10 to 20 years, phenomena in the ionosphere. Though it's a very old science, there are still newer and newer phenomena being discovered. So here, usually we have been talking all the time only up to F1 layer and F2 layer, but this is a situation where an additional layer above the F2 layer as F3 layer is obtained. This is usually seen only at equatorial and low latitudes, and the main reason for that is attributed to the E cross P drift that we discussed, because there is the electric field in the eastward direction driven by the dynamo action, and the magnetic field is in the northward direction, and therefore the plasma undergoes a vertical drift, and therefore it goes to a region where the loss is very small, and therefore the plasma density can increase, and that leads to the presence of the F3 layer. This has been studied in very great detail over a large number of low and equatorial latitudes. This is a recent paper in 2014 by Nayak et al. From the Indian Institute of Geomagnetism, published in Journal of Geophysical Research. And so it's an interesting new feature. Here it's also shown another feature which is written as STF4. ST standing for storm, and for storm time, sometimes even still another layer above F3 layer or F4 has been observed from a South American ionospheric observatory by name Tucumán in Argentina. So such new features are being discovered, and what the explanation for that is being thought by, and some mechanisms are being proposed. So with this, I conclude this talk on ionospheric measurements and phenomena. So in this presentation, I have used materials from scientific research papers, books, and websites. I am thankful to all for this. I also thank all